Hello, we are Team RoverOva from VSB Technical University of Ostrava, and this is our rover K3P4. Our team was formed at the end of 2016, and since 2018 we have participated 5 times in the European Rover Challenge, once in the University Rover Challenge, and once in the Anatolian Rover Challenge. Our team currently has 10 members, and we meet twice a month to manage our tasks. The work is organized through a Kanban board, where each team member is responsible for subtasks on each subsystem of the robot. We design our rover in Creo-parametric with its product lifecycle management tool Windchill, which allows all members to have up-to-date 3D models and documentation. Our workshop is equipped with several 3D printers, a bench drill, and handheld power tools. Therefore, in order to produce parts in-house, mechanical design is mostly focused on 3D printing or on parts that do not require heavy machining. The rover can be controlled via an 868 MHz RC transmitter or via Wi-Fi. If there is no signal from the RC transmitter, the rover will automatically switch to Wi-Fi. Video from IP cameras and webcams is transmitted via Wi-Fi. These cameras have high resolution and 4 times optical zoom. However, Wi-Fi may slow down the video transmission depending on the signal's strength. Therefore, we also implemented analog FPV cameras. Video from analog cameras is transmitted over 5.8 GHz band. Multiple analog FPV cameras with a video signal switcher are used for low resolution but real-time feedback. With these systems, even if the rover loses Wi-Fi signal, we can still drive the rover with visual feedback, which allows us to finish missions even in environments without line-of-sight communication. The Wi-Fi and analog video have range of about 1 kilometer. The RC transmitter can control the rover to up to 10 kilometers. The cameras, along with real-time 3D visualization, provide good situational awareness for the rover operators. The rover's mobility subsystem consists of a chassis with rigid swinging suspension. 4 wheels have integrated hub motors with planetary gearboxes. There are also 90-watt DC motors with planetary and worm gearboxes that can steer the wheels independently. The vehicle can thus be driven in several configurations. We have designed this suspension with rigidity in mind. Our 3D printed tires help the wheels gain the traction they need and provide a terrain-specific ride. The tires, together with the swing arm suspension, gives the rover good off-road handling with relatively high top speed. The mobility subsystem, without additional modules, weighs 35 kilograms, can overcome obstacles 20 cm high, and ride on inclines of up to 40 degrees. The electronics in the rover are divided into 2 circuits, one for motors and second for logic components. The emergency stop button disconnects batteries from both circuits. At the heart of our rover is a Jetson Xavier NX computer, which communicates with various microcontrollers in additional modules. Power distribution boards and driver boards are custom designed and allow us to fit all necessary electronics even in tight spaces. The rover is equipped with a 6 degrees of freedom manipulator that was designed with 3D printing in mind. 2 of the joints are utilizing custom 3D printed cycloidal gearboxes. We have tested the arm in various manipulation tasks. For example, here in our lab, the operators are controlling the arm to use a door handle, fully open the doors and drive through tight spaces. The arm is capable of grasping handles and pulling on drawers. The operator can utilize multiple ways of controlling the manipulator: direct teleoperation with an intuitive human-machine interface, driving to safe positions, or using inverse kinematics. With this capability, the arm can perform all of these manipulation tasks, for example grasping objects, delivering objects, turning screws and rotating valves. All of this is observed by the operator with multiple camera views. The arm is also capable of more fine control that allows for operating joysticks. The arm is also precise enough to insert a USB connector and to type on a keyboard. The arm itself weighs 9 kilograms and can grasp and carry objects of various sizes weighing up to 5 kilograms or pull heavier objects. During the science mission, we will collect soil samples to evaluate the defined hypothesis and to confirm the suitability of the selected landing zone for the planned manned mission. We have designed a laboratory module to conduct the tests. The module will store the selected amount of soil in bins. The module also includes a container for placing the rock sample. Weigh sensors are also included to measure the weight of the samples collected. For depth sampling, the rover is equipped with a special module. This module can take samples from depths up to 350 mm. Once the necessary samples have been taken, they are also placed in containers and weighed. To complete the probing task, the rover is equipped with a SCARA module. The module is located on the side of the robot, has a total of 3 degrees of freedom and an end effector with the required dimensions for gripping the probes. The module also includes a tray for placing found probes. We are developing a drone for the ERC competition to detect potential obstacles for the rover's movement. The drone will include a camera that will allow a visual inspection of the Mars yard and take photographs from the desired locations. We have been developing our rover for 80 years, and every year we recruit new members who want to improve their skills in robotics, mechanical and electronic part design. With new members come new ideas that help us continuously improve our rover, and the ERC competition is a great way to validate our improvements as well as new and exciting members of our team. We've made a lot of improvements to our rover and it was an honor to introduce it to you. We are ready to take part in the next edition of the ERC. We look forward to meeting you again.